A transit. When a smaller celestial body passes across the face of a larger one, hiding a small part of it, appearing as a small dot traveling across the larger body. On May 9th, the planet Mercury transits our Sun, passing between it and Earth. This rare celestial event happens only about 13 times a century. The 7.5-hour phenomenon is an astronomical wonder, but also provides a scientific opportunity to study the ultra-thin atmosphere or exosphere of our solar system's smallest planet.
Well, good morning. Welcome to NASA headquarters in Washington, D.C. My name is Dwayne Brown with the Office of Communications. The 2016 Mercury Transit of the Sun is happening right now. And in this next hour, not only are you going to hear more about that, you're going to see some images taken earlier, sort of a play-by-play of what you'll be seeing. You're also going to hear the incredible science that researchers obtain when you have the celestial dance of a planetary body passing our nearest star. We have some of the nation's top scientists here in our studio. You're going to hear from them. And join the conversation. There's a lot of buzz when we have these type of celestial events, Facebook, Twitter, etc. And you have the opportunity to ask these scientists here questions, not only about today's event, but events that are happening about the future. And you're going to hear about future missions that are going to explore the solar system and beyond. Send your questions in at #AskNASA. And let me just, as a note here, do not look directly at the sun. And you're probably going to hear our scientists talk about that also. Information is online, what you're here today, and much, much more at www.nasa.gov/transit. So let's get started. Let me introduce you to our scientists joining us for today. First, to my immediate right, someone who definitely knows about planets, Dr. Jim Green, the director of the Planetary Science Division at NASA headquarters. To my left, Lika Guhatakirta, heliophysics program scientist, also at NASA headquarters. Nikki Fox, project scientist, Solar Probe Plus mission at the Johns Hopkins University Applied Physics Laboratory in Lower Maryland. And Doug Huggins, Exoplanet Exploration Program Scientist, also at NASA headquarters. So let's talk about the planet, let's talk about the transit, and let me talk to, turn to here, Jim Green. Jim, welcome. Tell us what a transit is, and we're going to show some visuals from earlier and sort of walk us through what we're going to see here.
Sure. Well, what happens during a transit is really all about perspective. And when we here on Earth are looking at the sun and a planet will move in front of it, such as Mercury and Venus, then what happens is we see a transit. Now for Mercury, it is inclined in its orbit by 7 degrees from us. And so that means it misses the sun from our perspective many, many times. This is why we only see it 13 times a century. So this is a great transit and we're really excited about it. Now my first transit that I saw was on May 9th, 46 years ago. I wish it was only 16 years ago, but 46 years ago in 1970. And I did use a telescope with a protective lens. And that's very important for everyone to do.
And Jim, I believe the image that we're seeing now is the most recent, latest image of, and we see the little black dot. I think that's your planet. And, you know, let me just talk to you about an incredible mission. You've got a lot in the planetary world of Messenger, unlocking the secrets of this innermost planet in our solar system. Tell us about what we've learned about Mercury.
Well, you know, in the 70s, we flew by Mercury several times with the spacecraft Mariner 10. But it wasn't until 2011 when we got a fabulous spacecraft called Messenger in orbit around Mercury. For the very first time, we orbited this planet for more than 4 years. It was absolutely beautiful. So if I can have my first movie, what you're going to see is a false color image of Mercury. The colors and the variations tell us about those impacts. It's all about the minerals that are laying on the surface from those impacts. More of the yellowish colors and orangish colors, those are very volcanic. So what's happening when we look at these this is a very moon-like object, many different impacts, and a really spectacular one to study up in great detail. Now, another thing that we learned about Mercury from Messenger is let's look at its polar region. And how we do that is Mercury goes around the sun in 88 days, that's its 1 year. It also spins on its axis about 58 days. And from an elliptical orbit that Messenger was in, it could take an image of the polar cap, the north pole of Mercury, on every orbit. And from that, we can piece together this movie I'm going to show you. Now, what's really exciting about the movie that I want you to notice is those regions inside of craters that remain dark. So as you can see here in this movie, as the sunlight and the day on Mercury changes over time, you can see that many of these craters in the northern hemisphere are in permanent shadow. This is really exciting for the simple reason that we now find material, and we believe it's water, along with other volatiles that are laying inside these permanently shadowed craters. The temperature of Mercury all around it is scorchingly hot, more than 700 K, or 700 Kelvin we call it. This is hot enough to melt lead. But inside those permanently shadowed craters, it's some of the coldest regions in our solar system. And so water and other volatiles can remain. Now, this is the same kind of material like comets and asteroids that bombarded our Earth over the last 5 billion years. So it's a material of great interest to us. We'd like to get into one of these craters and take a good look at it. And Messenger has found those regions on Mercury where we're going to perhaps in the future go back to and take a good look at.
If you're just joining us, welcome again. This is NASA headquarters, Dwayne Brown. We're talking about the Mercury transit of the sun. Send your questions in. Social media. Hashtag Ask NASA. We have 4 of the top scientists here at NASA headquarters studio to answer your questions. Hashtag Ask NASA. We're going to have our first question. Jim, what type of Mercury science is done during a transit?
Well, when we observed Venus and Mercury for the very first time, we wanted to know how far away these objects were. And on Earth, you can observe these transits from various locations and therefore get a different perspective. So that told us about how far Mercury is away from the Earth and how far away is from the Sun. It gave us, for the very first time, a distance scale. And from then, we wanted to know much more about what Mercury looked like. Now, today, what we're doing is we're using telescopes to examine the atmosphere. Actually, we call it an exosphere because it's very thin, this outgassing that occurs at Mercury, and try to understand what it really is like. What are those gases? We know there's sodium there. We know there's potassium. There's all types of what we call trace gases, argon and other things that are being emitted by Mercury. And in fact, Messenger found out that over time, we believe Mercury continues to outgas and shrink. This is another fascinating phenomenon that we're not quite sure what's happening here. So those initial observations that we'll be making from Mercury today will tell us much more about those exospheric gases.
Thanks, Jim. And we're going to come back a little later in the program and talk more about Mercury. But this is about the sun. And I tell you right now, there's Dr. Lika Guhatakirta. I hope I got that right.
Pretty good.
We're going to say Lika.
Pretty good.
We're going to talk about, Lika, tell our audience, explain to the audience the difference between a transit in an eclipse? Because these types of celestial events, the public they go wild about this stuff. And I know the scientists really look forward to these types of things.
And they are pretty awesome. Of course, nothing like a total solar eclipse. So in astronomy, we use words like occultation, transit, eclipse. And a transit is simply, and so what happens here is two celestial bodies approach each other from our vantage point. And so during a transit, as Jim has already explained, what you see, a smaller body, celestial body, gets in front of a larger body cutting across the disk. And so the size of the two are distinctly different. Mercury is a dot, Sun is huge. During an occultation, what happens, and remember, this is our vantage point from planet Earth. During an occultation, what happens is that you have a larger body essentially in the middle, occulting a smaller body. So that object in front is hidden from our perspective. That's occultation. Now what if this object that we are trying to observe and the body in between have the same angular size? What happens then is a transit, it's an occultation, but what we call it is an eclipse. And that's what we see when the moon actually comes in front of the sun. Now I want to show you a picture to kind of drive this point home. As Jim mentioned, perspective is very important. So the perspective I laid out is from our planet as if we are watching these two bodies. Now let's run the first movie. And if you look at this movie, of course, that is a pink sun, and of course we take images of the sun in different wavelength and colored them. That's why you see this artificial color. It's in extreme ultraviolet. And what you see, if the movie plays again, you will see this relatively large dark disk going over. It's not the size of Mercury or Venus. We are used to seeing those transits. So what the heck is that? What happened there is that one of our spacecraft, Stereo B, in February 25, 2007, essentially went across the sun. And this was the lunar transit as observed by Stereo, which was 1 million miles away from our perspective of the moon. And therefore, Stereo's telescopes were looking at the moon, which was about 4.4 times smaller. And that's what you saw. I mean, it's kind of really alien-like. It's as if we are in a different solar system. So that's what you saw there. Now, transits, eclipses are very important for scientists, especially solar scientists, but you'll hear later about exoplanets too, for calibration purposes. So we calibrate our telescopes, our CCD detectors. We point our telescopes because, for example, Mercury is fixed in space, and we can point actually a telescope and get better pointing. Now, I'd like to talk about eclipse.
I was going to ask you that same question. There is something really special happening next year, and the whole country, I don't want to spill the beans. Tell us about what's going to happen in 2017.
So this is, yes, as I was saying, transits are great, occultations, you just don't see the other guy, kind of sad. But eclipses, especially a total solar eclipse of the sun, is absolutely out of this world. And this grand spectacle is going to pass through the entire mainland of USA on August 21st, 2017, next year. Coast to coast, starting at coast of Oregon all the way to South Carolina. 12 states, about 65% of America will see a partial eclipse of the sun. So if I can have the movie running, what happens during a total or a partial solar eclipse? What you're seeing there is essentially moon's shadow, and there are two shadows here. The triangular with a black dot is the umbral cone. That's the deepest shadow. That's where the moon's shadow in that path is completely covering the yellow disk of the sun. That's when you will actually see the solar corona, and I'll come to that. But the lighter shadow is the penumbra, and that shadow, wherever that is passing through, you are going to see a partial eclipse of the sun, which itself is something to behold. Now, this eclipse is actually really, really interesting because something like this hasn't happened on the mainland of USA for almost 100 years. And now we have a different generation of young kids, you know, with access to technology, mobile phones, social media. They are going to be able to watch this eclipse in a way nobody ever has. And I call this the Generation Eclipse. And this movie here shows that if you took yourself, which you must, to the path of totality, then what you would see is that beautiful silhouette that you're seeing. That is the corona. That is the outermost atmosphere of the sun. And that's what you're going to see. It's beauty to behold.
And I'm quite sure as time goes on, there's going to be more information promoting and also talking what's coming down the pipe for next year, because this is going to be not just nationwide, but a global type of interest in this.
Absolutely. There is a lot of work going on, and we will have a dedicated Eclipse website up relatively soon, so please stay tuned.
And if you're just joining us, welcome to NASA headquarters. We're talking about today's transit, Mercury transit of the sun. I believe we have, if we can put up the latest image of that transit. This was taken not too long ago. So this is what we're talking about today here at NASA headquarters with some of the top scientists here joining us to talk about not just the transit, but the science and future missions. Social media, there's a lot of conversation, a lot of questions. This is an opportunity for you to hear it from the experts in their fields, in their respective communities. Send in your questions, #AskNASA. Now, let's talk about, let's go to a social media question, because I'm excited to get to a mission, one of the future missions that we're going to talk about. But Lika, one of the social media questions, and we get a lot of these, is we hear about astrophysicists. What is a heliophysicist?
What a question. Heliophysics is a brand new word that we came up with about 10 years ago, really to describe the sun as a star and its impact on our planet and all other planets in the solar system. So it is all about connecting our sun to how it impacts life or anything else in the solar system. It is the connection, and that's heliophysics.
Well, let me thank you, Lika, and keep sending those questions in at #AskNASA. So we talked about the transit, but there's a mission that is pretty incredible, and we have the project scientist, I believe, did I get that right? Dr. Nikki Fox. This mission, talk about this mission. It's going to launch in 2018. It's unprecedented with the technology, and it's going to see the sun pretty up close and personal.
It is. Thank you, Dwayne. Yes, so Solar Probe Plus is the coolest, hottest mission under the sun. It will launch in 2018. By the time we launch, it will have been 60 years in the making. It actually is a mission that predates NASA. When the committee got together to decide what big things NASA would do, this was one of the 8 missions, and it's the only one that hasn't flown yet, not because of the tremendous support for it, but because we haven't had the technology until now to allow us to do it. So it's a very unusual looking mission, and if we can run the first graphic, please, you'll see she's a very unusual looking spacecraft. In the front there, a big heat shield, our thermal protection system that will keep all of our instruments working at a temperature very close to room temperature, even though the front side of that shield will be seeing temperatures of about 1,300 degrees, but those instruments are at room temperature. You see just how close we get to the sun. The big key for us is getting up close to the sun. And if we had the sun and the Earth a meter apart, Solar Probe would be just 4 centimeters away from the solar surface at her closest approach. We get there using a novel mission design. We have 24 flybys of the sun. We have 7 flybys of not Mercury, but Venus, that allow us to do gravity assists and lower our closest approach to the sun on each of those 7 flybys of Venus. Even on our very first orbit, we are well inside the orbit of Mercury, the closest man-made object ever to come to the sun. So it's exciting, the science is amazing, and we can't wait for 2018.
And Nikki, what are some of the biggest questions, or hopefully some of the biggest answers you hope the science community hopes to gain with this future mission?
So there are so many questions, obviously, that we will answer, but the two that have boggled scientists' minds for hundreds almost of years are, in fact, since we discovered the corona that Lika talked about, when it was discovered, the big puzzling thing was it was so hot. It was way, way hotter than it should be. The surface of the sun is about 6,000 degrees. The corona at its maximum is a couple of million degrees. That shouldn't happen. It's like water flowing uphill. You've got a surface, and then as you get further away from it, it should get colder, but it just doesn't. This is a mystery, and there's no theory that has yet been able to explain why that happens consistently. The other thing is, as you saw in some of the movies, and I know some that Lika will be showing in next, that outer atmosphere, the corona, streams away continually from the planets and from the sun, and it bathes all of the planets. So in the same way that Lika was saying, the sun has an effect on the Earth, and if we run the movie now, you can see some of the dynamics of the sun. Just as the sun is very dynamic, it's throwing all this material, it interacts with our planet, and so it's extremely important to us that we can understand the dynamics of the sun, not only to explain why the corona is so hot, but also to explain why this material is continually coming away from the sun. It doesn't stay with the sun, it gets to a certain point and it just leaves and it's out of there.
Ladies and gentlemen, you're listening to NASA television and a program talking about today's Mercury transit of the sun. We're here with scientists that are talking about not just the celestial dance with Mercury and the sun, but future missions and the incredible science that they're going to get. A lot of questions are coming on social media. We're going to try to get to as many as we can. Send those questions in to #AskNASA. And again, if we can get the image up, this is the latest image of today's celestial dance, and you can see the little dot. Ladies and gentlemen, that's Mercury. And of course, the big ball there is obviously the nearest star, our sun. So you'll hear more about that. Keep those questions coming in at #AskNASA. Let me throw out another social media question from Reed Lawson, maybe for Lika or Nikki. How long do transits last?
The order of what, 7 hours?
Yes,
It depends on when the transit is occurring, which planet it is. So it's all about geometry.
Math.
Math, absolutely. But it's simple math.
Okay, so we've talked about the planet. We've talked about the sun. There's this incredible thing going on that's got the public excited. They're called exoplanets. And Dr. Doug Huggins, the expert in exoplanets. Doug, transits, they're really cool to watch. Obviously, you know all about them. But there's an interesting science that can come about that when we talk about exoplanets. Talk about that.
Well, that's a great question, Dwayne. There's probably people out there right now that are thinking, well, wait a minute, this is Mercury transiting the sun. This is all about our own solar system. What can that possibly tell us about the planets that lie around other stars? Well, in fact, although the transit of Mercury is a fascinating and unusual occurrence right here in our own solar system, in fact, it's a great illustration of one of the best technologies, one of the best techniques we have to detect planets around other stars. If we can have the first graphic. Now, we've already talked about a transit is when a planet passes in front of the sun, and when that happens, we know that the light from the background star, in this case the sun, gets blocked out. And you can see this curve here, which is what we call a light curve. When the planet passes in front of the sun, the brightness drops a little bit. Well, in fact, that's the same thing is true if that planet is not a planet in our own solar system, but a planet orbiting another star. If the planet has an orbit where it passes along our line of sight to the star, when it passes in front of the star, it will transit the star, and in fact, we'll see a little drop in brightness. Now, of course, the problem is stars are enormously further away from us than our own sun is. So, in fact, when we see a transit of an exoplanet, we aren't able to see the planet itself. In fact, we don't see the planet at all, and the star itself is not a disk, but in fact, it's just a point of light. Nevertheless, when the planet passes in front of that star, what we see is a dip in the brightness of that star. And if we can measure the brightness of the star, when we see that dip, we know that there is a planet in orbit around it. And that's been a great technique for finding planets around other stars.
Well, there's a mission that has really brought a lot of attention to exoplanets, something I know is near and dear to you, Kepler. What has happened to the scientific community with the outstanding and unprecedented findings from Kepler? Explain what Kepler has been doing.
Well, you're absolutely right. The Kepler mission has been very much in the public eye over the last several years. Kepler, I should point out, was the brainchild of scientist Bill Barucki from NASA Ames Research Center in the San Francisco Bay Area. He had the idea that NASA should fly a mission that would use the transit technique to look for planets around other stars. In fact, you'll realize that that is what ultimately became the Kepler mission, which was the 10th mission that was developed under the Planetary Science Division's Discovery program. And in fact, it launched in March of 2009. It operated from the time it launched, it operated for more than 4 years, staring at a patch of sky. If we can see the graphic here for the Kepler mission, it stared at a patch of sky that's about the size of your fist if you were to hold it up against the sky, in the constellations of Cygnus the Swan and Lyra the Harp. And in fact, what it did is it stared continuously for more than 4 years at about 150,000 stars in that field. What it was looking for was that telltale drop in brightness that is indicative of planet transits. And in fact, it was tremendously successful. It found an enormous number of planets. Today we know that the Kepler mission has discovered more than 1,000 planets orbiting other stars. There's an additional 3,700 or so additional planet candidates, which are signals that give every indication that they may be exoplanet transits, but in fact they need more follow-up observations or data analysis to actually confirm that that's the case. One of the things that we know is, that we've learned from the Kepler mission, is in fact when you go out at night and you stare up at the sky, pretty much every star you see in the night sky has at least one planet, probably more planets than that. Now, if you're in Washington, D.C. and you can only see 4 or 5 stars, then that may not seem so impressive. But in fact, if you go out in the country where you can see all the stars laid out above you, it's a pretty amazing thought.
Okay, so we're going to, let's get back to the transit, and we're going to come back to the planet and the missions and all that. If you're just joining us, welcome to NASA headquarters. We're talking about the Mercury Transit of the Sun. And what we're going to do now, we're going to put up the latest visual received today. And we're going to ask, we're here at NASA headquarters studio with NASA scientists, a scientist from the Applied Physics Laboratory. I'm going to ask Lika, and then maybe Jim and Doug. We're going to have this looped image of Mercury. Explain to the audience what you're seeing. How can you describe it in 30 seconds or less?
So that is, I guess, a real live image from Solar Dynamics Observatory, and you are actually seeing the transit in progress, and that little black dot, I can say that it's Mercury only because it's so uniform. Sometimes you can have sunspots that are much bigger than that, but I've never seen such a round and perfect sunspot. So that's what you're observing, the little dot Mercury transiting across the face of the solar disk from HMI instrument.
And Jim, from a planetary perspective, what are you seeing there?
Well, we know that Mercury is our smallest planet. It's larger than the moon, but still smaller than Mars, so it fits in between there. But when I look at an image like that in its breadth, I also are looking at the sunspots, as Lika mentioned, because even though the sunspots are approximately the size of Mercury as we see it in this projection, they're absolutely enormous. In fact, they're probably larger than the Earth that's sitting on the sun. And that's because Mercury is, although it's close to the sun, it's not that close. It is still in its orbit, going around, even though the gravity from the sun is pulling on all our planets. It has its own basic energy, and the centripetal force balances that gravity, and it allows it then to make its nearly circular orbit around the sun. So it's a beautiful set of observations we're making today.
Okay, we're going to talk more about Messenger in a moment, but I just want to remind our viewing public, do not look directly at the sun. You have to have protective measures. You have to have the specialized telescopes, but please do not do so. Keep that channel turned here. You're going to see and hear more about it. So, Jim, let's talk more about. We see Mercury, little dot. These images were captured. You know, these are the latest images. Pretty fascinating. Messenger. Tell me about the mission to Messenger and the challenges that you had, and just how successful in the answers of that mission.
Well, Messenger is a principal investigator mission. Sean Solomon was the principal investigator of it. It was launched in 2004. But it didn't just travel straight to Mercury. It actually had to gain enough energy and actually try to get into an orbit that is much more like Mercury. And to do that, it first did a flyby of the Earth. It then did 2 flybys of Venus and 3 flybys of Mercury until it could actually sort of match the orbit of Mercury. And then in 2011, it got into orbit. And from 2011 to 2015, over 4 years, it made spectacular observations. And if I can have my next movie, I want to show you Mercury in a completely different way. Now, this particular set of observations are Mercury colored in altitude. The Messenger mission had a laser altimeter on it, and hitting Mercury with laser beams allowed us, based on the timing of each of those return signals, to determine the height of these features. Now, this is Mercury like we've never seen it before. We can see the highlands that is shown here in the yellow and orange colors and some of the red colors. More of the lowlands are in the greens and blues and purples. So you can see this huge height difference. Now that's about 7 or 8 kilometers in difference, which is quite astounding. Here on Earth, that's a distance that's higher than Mount Everest. And so this paints a picture of Mercury quite different than what we showed earlier. The impacts are obvious. The highlands and the lowlands, some of these areas where we've seen craters are actually been now filled in with molten material, and we get this beautiful height variation.
So Jim, and the folks, again, thank you for sending your questions. We're going to take a moment to answer some of those. And a lot of the questions on social media, send those questions in, keep them coming. Hashtag Ask NASA. Jim, about your planet, Mercury. From Carolina, how do you calculate the dimensions of a planet when observed by a transit?
Well, when we observe an object in the sky, our planets, and having it during the transit, it's really all about geometry. You know, it's really all about knowing the distance to the planet that we've calculated in perhaps other ways. And one way that I mentioned earlier is to observe a transit from 2 different locations on Earth, very different locations. So that's like putting your finger out and then one eye on the other, and you watch your finger jump. And that enables you then to triangulate and through geometry be able to get the distances. So once you have the distances then you are going to do timing. You're going to understand when the planet's surface starts being seen during a transit and when it ends. And so those things are timed very perfectly. You know the distance in its orbit. You then can calculate its size. So that's one method that we've used in the past.
Thanks, Jim. We got a couple more questions. I want to remind folks that we're here from NASA headquarters taking questions from #AskNASA about Mercury transit of the sun. NASA scientists and applied physics laboratory scientists are here to answer your questions. And let's stay on Mercury, Jim. You know, how does the transit affect the temperature, surface, and atmosphere of Mercury?
Well, as I mentioned, the temperature, the hottest Mercury gets is 700 K or 700 Kelvin. Now that's incredibly hot. It's hot enough to melt lead. It's hot enough to melt a lot of things, from water to all sorts of what we call volatiles. But Mercury hasn't been completely vaporized. The only way to completely vaporize Mercury would be to move it all the way to the sun and let the enormous temperature, the 5,800 Kelvin surface temperature of Mercury, disassociate all the atoms. So Mercury is still a very solid body. One of the things about Mercury that's also quite fascinating is it has a core that's approximately the size of ours, and here on Earth. And so we believe that it's a molten iron core. It generates a magnetic field. We've measured that magnetic field. We don't really understand how come a body as small as Mercury, and once again it's larger than the Moon, but smaller than Mars, has such a large core of iron. So that's one of the leading questions that we'd like to answer.
Okay, so let's go back to our sun, and I'm going to turn to Lika a bit. And Lika, while you're talking, we're going to put up some of the latest images again of Mercury doing its transit with the sun. Why do we study the sun?
Well, I don't know what else we would study. This is the star that gives us life. But that aside, I think the sun is actually, when I grew up and did astrophysics, you know, we were always told sun is a boring star. You hear about a solar constant like it doesn't vary. Well, yes, if you're only looking at it in the visible wavelength as we do, that's how the sun appears. Nothing could be more wrong, actually. Sun is not average, it's not a dwarf, it's not yellow, it's only yellow in one particular wavelength. Our sun is actually a turbulent, dynamic, magnetically variable star that pretty much drives every cubic inch of space in our solar system and everything in it. And it's the magnetic variability that makes the sun interesting as a star to study from scientific point of view, but it also actually creates some problems for us. This magnetic variability actually creates a condition called space weather.
Okay.
And this is, if I can get the first movie, what this movie will show is 6 years of observation from Solar Dynamics Observatory. And what you are seeing is images taken in extreme ultraviolet wavelength. And so clearly you can see that the sun is actually constantly moving, churning, dynamic. Yes.
So let me, I want to, because we're kind of running short on time here, but I don't mean to interrupt you. But while we've got that on, I want to pivot to Nikki, because what else to study but the sun, as you said, right? So we've got this incredible future mission coming up. Again, let's talk about Solar Flow Plus.
So we're going to go right up into that solar atmosphere. You know, we will be in the corona, the outer region of the corona. And if we run this video, you'll see we have all the right instruments to be able to go and make the measurements. So you'll see some of the antenna coming out now. We have a camera that's going to be taking pictures of what the spacecraft's seeing. We have instruments that are measuring all of the different particle populations. So the dynamics that you see in this movie and the one that Lika had just shown will be right up in there. We've learned so much about the sun over you know, the last few decades by looking at it. but you only learn so much about looking. You want to be able to use all of your senses. We want to go and touch it. We want to go and listen to it. We want to go taste it, if you like. We want to go right up to that sun and really find out what's going on. If you imagine you're on a boat on the sea, you know you're moving, but there's all these eddy currents and all this fascinating stuff that's going on below the boat. If you hop out of the boat and go down, you'd actually experience that. So that is what we're doing. We'll be going right up and we'll be looking at all of that fine scale. The devil is in the details, that fine scale physics that is down to be able to answer these questions about why the corona is so hot and why the solar wind moves so fast.
Fascinating. And Lika, again, you know, studying the sun, incredible, explaining heliophysics, new Solar Probe Plus mission. But we've got another mission. Let's pivot over here to Doug, something called Tess. Talk about that.
So Tess is the Transiting Exoplanet Survey Satellite, and it's a complement to the Kepler mission that'll be coming up in just launching in late 2017. Tess complements Kepler. So if you think about Kepler, Kepler provided, the whole thing about Kepler was, it was to provide the census of planets. It need to tell us things like how common are planets, what's the distribution in their sizes, what's the distribution in their orbits, and just sort of the demographic information about the population of planets in our galaxy. Now, Tess kind of turns that around and says, okay, what's our neighborhood like? And Tess is going to do an all-sky survey. So instead of just looking at a single patch of the sky, Tess is designed to look at the whole sky. And it will basically look at the nearest stars and the brightest stars as seen from Earth. So we'll be looking for the planets that are the transiting planets, I should say, that are in our neighborhood. Now, why do we care particularly about the planets that are in our neighborhood? Well, those are the planets that are going to have the most promise for us to follow up with future observations, with telescopes like the James Webb Space Telescope that'll be launching in just a few years. We'll be able to follow up and begin to take measurements that will give us an indication of what the atmospheres of those planets might be made of. Then even further down the road, a future, what we call a direct detection mission, a mission that's actually capable of blocking out the light, the overwhelming glare from the primary star, and being able to see the feeble reflected light from the planet that's orbiting right next to it, and being able to figure out from that things like, again, what the atmosphere of the planet's made of, what its temperature might be like, even possibly what its ground cover might be made of. And of course, these are all key things to answering what I believe one of the most enduring questions of humankind is, are we alone? Is there life out there? So it's really, the direction that it points us in is really very exciting.
Fantastic. If you're just joining us here at NASA headquarters, we're here with scientists talking about today's Mercury transit of the sun. Send in those questions at #AskNASA. We're going to put up right now the latest image and visual of Mercury during the transit. I like to call it the planetary dance of our nearest sun. Nearest star, I should say. And I'm going to ask Lika, I believe you have one more visual to sort of, let's get back to the sun and the transit, and then we're going to go over to Nikki with another visual, and then we're going to try to get another one or two questions. Keep those questions coming. If we can't answer them in this program, we'll get to them as quickly as we can. Again, you're looking at the latest images or visual of the transit, and I'll toss it back to you, Lika. You were making some incredible comments about the sun, but I believe you have another point to
so
make.
I was trying to make the point about space weather, right? We actually, what you have seen, that the corona exit, that there is continuous blowing out of solar wind. And every 11 years, the sun goes through this active phase of solar cycle, and you have what's called solar flares, coronal mass ejections. These are huge amount of mass, momentum, energy that is expelled into solar system. And when we get this directed towards our planet, then our planet's magnetosphere starts interacting with this magnetic field and particles. and it can cause aurora, the beautiful display of sunlight. That is the benevolent side of such a storm, but then it can affect essentially our power grid and can do serious damage to that, GPS navigation error, satellites malfunction. If there are astronauts doing EVA, there can be radiation, extra radiation dosage that they will receive. But it's not just our planet. I actually want to go back to Mercury, something that Jim didn't say. So what space weather does is Mercury has this incredibly dynamic magnetosphere where solar wind interaction with that shows 10 times the reconnection rate that we see on our own planet. MAVEN, another mission, Mars, we are seeing solar wind, coronal mass ejections stripping away essentially the atmosphere of another planet. And going back to Exoplanet, I would say that we really need to study the Sun, Earth as a prototype system to see how an orbiting planet like our planet harbors life in front of a stellar object. I mean, this will give us ideas of even what we are looking for. So this is an incredibly rich time, I think, in NASA history, all of us working together.
So ladies and gentlemen, you can obviously see that Lika really loves what she does, and she's very good at it, as all these folks are. So we're coming near the end, but I want to go back to Nikki. I believe you have another sun image, and we can talk about that. We're talking about the sun in transit.
I do. I have one of my favorite solar images, yes, if we can run that one. But again, you know, we're just so excited to be going finally to the last region. Now New Horizons has been to Pluto. It's really the last region of our solar system, and it's really the most important. As Lika said, the sun is the star of our show. It is always changing. It is always dynamic. You never know. One of the great things about being a solar scientist, when you get up in the morning, you never know what you're going to be studying. It just changes all the time. The wonderful thing about Solar Probe is, since we are a 7-year mission with 24 flybys, as Lika noted, the solar cycle is 11 years. So we are going to be seeing all kinds of different sun. We'll see, as she said, the flares and the coronal mass ejections and the big activity that's often associated with solar maximum. But we'll also be seeing a quieter sun, where, in fact, you can actually learn a lot from very quiet conditions. We'll be seeing high-speed streams, all kinds of wonderful things, and we'll be right up, even closer than that tiny dot. There will be an even tinier dot that will be Solar Probe Plus.
Well, and I definitely want to give a shout out to the Johns Hopkins University Applied Physics Laboratory, building, designing, and all kinds of really cool things that they're doing out at APL. What is, and I'm going to come back to you for a website for Tess, which is the new mission, but is there a website to learn more about Solar Probe Plus?
Yes, www.solarprobeplus. Actually, I'm sorry, www.nasa.gov/solarprobeplus.
Very easy. And for Tess, we talked about that website, Doug.
It is tess.gsfc.nasa.gov.
Okay, let's get back to putting back up the latest image of the Mercury transit of the sun. Today, we've been talking about that for the past hour. Lots of science. We're here with scientists talking about the transit, talking about what it means for science, talking about future missions that are going to explore the solar system and beyond, because we're out there. This is what it's all about when we talk about science. But before we sort of wind down here, we're still getting a lot of questions about Mercury, and I'm going to turn to our planetary director here, Jim Green. How fast is Mercury traveling, and what's the surface of Mercury made of? I believe you talked, but talk more about detail about that.
Well, I don't know exactly how fast Mercury's traveling. We'll have to look that up. It's one of those facts that's important to know. But each of the planets have certain velocities that they must maintain to be able to maintain their orbits as they go around the sun. Mercury is a rocky planet, as I've mentioned before. And so the rocks are primarily silicon-based, but there are also different types of materials. we'll see everything from aluminum to iron to lead, etc. But indeed, it's a rocky planet that if you could actually go there and survive the enormous heat, you could walk on the surface.
Fantastic. And again, if you send your questions in at #AskNASA. If we don't have the answers today, I can guarantee you we'll get them for you, and we'll try to answer all of the questions because they keep coming in about Mercury and the transit. And I'm going to ask that we put up again the image, the latest image of the transit, the Mercury Transit, doing its celestial dance with our nearest star. And you're hearing the science, you're hearing future missions and everything. And you've also heard, why do we care? Alika, you were talking about all the things with the sun and how it affects the Earth. And I just want to thank the folks here and also thank the folks that are watching this and sending in your questions. And we got time for a couple more questions, and then we're going to come back to Mercury, a sort of tribute, because it has been one of NASA's most successful missions, and we're going to see a sort of a salute to that. How big does Mercury look compared to an average sunspot? I got to talk to my heliophysics person here. You talked about that earlier.
I am looking at that. I'd say pretty average. Because sunspots come in all different shapes and sizes. So Mercury is pretty small. It's what, about 10 arc seconds or so. Sunspots can be quite large. So, you know, I don't have an average number. The distribution is large for sunspots. You can have very, very large sunspots. These are called naked eye sunspots that could be actually visible. So Mercury, for example, you can't see from our planet right now. You need a telescope to see it, right? Transit of Venus, I think we could see, which was about 60 arc seconds or so. So you need a large sunspot. So Mercury might be on the smaller side, but I couldn't tell in terms of average because the distribution is large.
So, but sunspots could be gigantic, enormous,
absolutely,
even larger than Jupiter and anything else.
Yes.
So where are we in the solar cycle right now?
We are actually tipped over, you know, beyond maximum, sort of on the descending part of the cycle. And this solar cycle has been fascinating, as we must know, right? I mean, everything about the sun has been unusual since almost 2008-9 time frame, when we had the deepest solar minimum that we have experienced in space age. And the question now is, a deep solar minimum has its own implications for space weather, just like Nikki was saying. So while you do not have activity on the sun, the weak magnetic field allows for the invasion of cosmic rays, galactic cosmic rays. And so if you are doing any kind of deep space exploration, these galactic cosmic rays can be lethal. So, you know, space weather sort of happens at all phases of the solar cycle.
Does Mercury cast a shadow on Earth during the transit?
I don't think so.
Well, just like as Lika showed, the black shadow is the direct one, and that would be if Mercury, if we were in a location where Mercury would cover the whole disk. But as Mercury moves away, that outer shadow, that penumbra, must be what we are seeing, because then we can see the light from around the disk. And so, in a way, yes, and this is why the light goes down, as Doug showed in the transit. So there is a small shadow that it's casting, and we measure it when we measure the total light from the surface of the sun.
Fantastic. So, Lika, what's next? With the data that you all are getting today, what's next? What scientists would do with the data that they're going to get today?
So for solar physicists, we have several different spacecraft in orbit. SOHO, Solar Dynamics Observatory, and Hinode, which is also a Japanese NASA collaboration. I think all of these are taking measurements of Mercury essentially to do deep calibration of their CCD detectors, essentially measuring the dark current, you know, so that you can remove it from images to get more accurate description, quantitative profile of the images that you have taken. So that's a very, and we like to do it as often as we can, because with time, and most of our satellites are older than 5, some are way older than 5, and so detectors degrade, and so you want to continuously, if you have the opportunity, kind of calibrate that. And pointing is another thing also we do.
Fantastic. So ladies and gentlemen, you've been hearing scientists talk about Mercury transit of the sun. Let's put up what you're seeing right now is the latest image. That little black dot is, yes, that's Mercury, and of course you know what the big yellow thing is. That's our nearest star. I want to thank you all for joining us. Keep sending in those questions. We couldn't get to all of them. Tried to get to them as quickly as I can, but we will still get you those answers at #AskNASA. I want to thank our scientists. You missed a real treat if you didn't get this, but I'm sure that you can go online at www.nasa.gov/transit. You're here, more about the transit, what you've heard today, and much, much more. We're going to close with a tribute. We talked about the planet Mercury and, of course, the highly successful NASA planetary mission Messenger. So we're going to give a tribute to that with a video, but I just want to thank you all. Thank, again, our scientists. And always remember at NASA, science never sleeps.